Previously on the head of a pen.
The quarks in the second family are called the strange and the charm quark. Then there's a third family, the bottom and the top quark.
We think of quarks and electrons and so forth as tiny little points, but that description of nature has a problem, and there are infinities. If you say that the electron has no size, does that mean all of its charge is concentrated at a single mathematical point? If so, if you try to do the calculation of the electron self-energy, it explodes. You can't, you get an infinity. It tells you that there's an infinite amount of energy required to put all that charge in one point. So we all know in our minds that it must be that the charge is spread out in some way in space.
So to start with, everything is a model, and then experiment comes and tests it, and most models prove not to correspond to reality, and a few, usually one, corresponds to reality, and it becomes the standard model of that time. And that changes with time. And so there is physics and there is mathematics. Mathematics is the world of all consistent mathematical structures, and physics is, there is only one of these mathematical models that correspond to the physical world. And physics needs experiment to confirm a given theory. So when we propose several different theories, hopefully they can all be tested. Now, string theory can also be tested. For example, that the LHC, if these theories with large dimensions that I was telling you about are correct, then LHC will test these theories, and if it confirms them, they will be confirmation. They can lead to confirmation of string theory. Direct production of strings at the LHC is a theoretical possibility. Whether it's realized or not, only experiment can tell.
The other interesting thing about the string hypothesis is that these one-dimensional entities, like an electron has some piece of string, some one-dimensional entity that corresponds to it, they travel in something like 10 dimensions, or 11 dimensions if you want to include a dimension of time. Instead of traveling in the 3 + 1 dimensions of space-time that we're familiar with, these objects travel in and vibrate in 10 + 1 dimensions of space-time. Yeah. All right? And we don't see the other 6 or 7 dimensions because they are curled up or compactified so tightly that they do not become evident in our normal everyday life.
So imagine we have a one-dimensional universe. That is, everything we know propagates along this one dimension. Now imagine there's a knot in it. Can that knot propagate? I asked a string theorist this question once. I mean, and can you imagine complex sorts of knots which, if those two knots collide, they make a different knot? Well, in higher dimensional spaces, you can do stuff like that. You can have topological defects which have, sort of integer classifications. In other words, you might say a simple knot is a number 1 knot. A double knot is a number 2 knot. But you can't have a 1.5 knot, right? A knot is a knot. It's either the next level of complexity or not. So we see that particles have integer quantum numbers. Where do these integer quantum numbers come from? Space and topology, topological defects could, certainly, geometric objects in higher dimensions are described by integer type things. So we need something that gives us the mass of particles, their interaction strengths, their intrinsic angular momentum, their spin. This is a tall order for whatever theory you're going to come up with, but It certainly appears that the way theorists are thinking, it's along the lines of higher dimensional spaces and the mathematics that obtains there.
Strings are objects that are what they sound like. They're one-dimensional objects, and therefore they can exist in a multitude of states. They can be straight or they can be vibrating like the strings in a violin. For low frequencies they can have few vibrational nodes, and for high frequencies they can have many vibrations, and each state of the string corresponds to a different elementary particle.
Now, one of the early ideas from the 1970s was that, in fact, you could spread this charge out along a little piece of string. I think it's a kind of a interesting idea, but it has taken decades of the best minds and mathematicians and physicists working on this to realize that there may be no solution which allows you to describe particles in terms of little waving bits of string, whether they're open or closed on themselves or what have you. Now they've gone into higher dimensional representations of particles, so-called M theory, which uses like 11 or 10 dimensions to describe the world that we have. And in that theory, and this is what string theory has evolved to in this decade now, they have now realized that yes, there are solutions that could give us the world we know and love, but there are 10 to some huge number, like 500, 10 to the 500th different possible solutions to string theory. And now the challenge is to figure out, is there some principle that could allow us to select out the one solution out of 10 to the 500th which describes our world. So string theory is at a bit of an impasse, but to solve this particular problem. And I don't know what the future holds for string theory at all. I think we need more guidance from experiment. We need to know more about the nature of the world that we're in to restrict the space of possible explanations from string theory or whatever other theory lies beyond what we have now.
A massive particle could be vibrating not just in our dimensions but inside extra dimensions. This we would describe as, and the different modes of vibration of the particle inside the extra dimensions could be described as ordinary particles but of different mass, a variety of ordinary particles of different mass. So in fact the vibration of particles inside the extra dimensions give you a multiplicity of particles inside our dimensions.
It could be that the mass, the intrinsic mass of particles is related to even smaller constituents that they might have. If you take all of the protons and neutrons that you need to assemble a carbon nucleus, and you need 6 protons and 6 neutrons, and you measure their mass, and now you put them together into a carbon nucleus, you find that the mass of the carbon nucleus is slightly less than the mass of the 6 protons and 6 neutrons that you had to begin with. When those particles glom together into the nucleus, energy is given off in the form of gamma rays or whatever. This is the basis of nuclear energy, in fact, right? Is incredible amounts of energy. Now imagine, scale this up to hundreds of times more energy than we have in nuclear energy. And you can imagine that, well, maybe an electron is a very tightly bound, or the most tightly bound state of 2 other particles. And that the heavier versions, the muon and the tau, which are charged leptons like the electron, are just excitations of the electron itself. That's not impossible, I suppose. You could come up with a theory that does that. And likewise for the quarks, you could say quarks have substructure, and if you bang them hard enough, you could excite them into higher particles. And that could just be a manifestation of the binding energy, just like the binding energy of the nucleus, there could be this new force that binds together the particles into the ones that we know about. But once we hit them hard enough, we can break them apart into what they're made of. But we've tried, and we haven't seen any substructure yet in electrons or muons.
Hyperdimensional is that in order for them to be accessible at the LHC, there must be extra dimensions. Remember, extra dimensions explain why gravity is weak. It's one possible explanation for why gravity is weak. So in these theories, gravity is actually not that weak. If you look at gravity at very short distances, at subnuclear distances, at distances that LHC will probe, gravity is not intrinsically weak. It only gets weak if you look at it from far away, from large distance away. So because gravity is not intrinsically weak in these theories, you can actually see effects of gravity, such as black holes, at the LHC. So that's why having extra dimensions that are large is crucial to producing black holes at the LHC.
We know black holes exist. They're not just theoretical. We can see them in space. Big black holes with masses of many, many times the mass of our sun. In fact, at the center of our own galaxy, there's a black hole. You can see stars orbiting this black hole. They think it's around several times 10 to the 6th, several million times the mass of our sun. But the kind of black holes that we're talking about at the LHC are really, really very different. We know that if you get enough matter, enough mass energy density into a small enough place, a black hole has to form, right? And so there's the notion that we could do this because we're going to a new energy frontier at the Large Hadron Collider. If there's enough energy, we could create a black hole. But this wouldn't be a conventional black hole that exists in our three-dimensional, three-space, one-time dimensional world, 3 + 1 dimensional world. It would have to be a black hole in higher dimensions, and the reasons for that are mathematical. But you would have to have extra dimensions to create black holes, to allow black holes to be created at the Large Hadron Collider. And as Stephen Hawking has predicted, any tiny black hole like that would decay very rapidly, and we call it evaporate. That's a good analogy, but it's not really evaporation. It's just disappearing, basically, back into energy form. It wouldn't, wouldn't sit there and grow.